same as yesterday in terms of length. Okay, so Newton's second law, right? There's many ways to state Newton's second law. The first way is to say in a math speak that your net force, when it's not equal to 0, is equal to mass times acceleration. Right? So that's Newton's second law of motion. We can write it out in words if we need to. I could write it out, say exactly the same thing. So when the forces acting on the object so when your forces acting on the object are not balanced, right? So yesterday they were balanced, today they're not balanced, that your object accelerates in the direction of the net force. So that brings me to the picture. Oh, yep. Forgot to move the camera back. So when you look at the picture there, I wanted to put the picture up there just to emphasize the relationship, right? So you have the boy who's the same in both pictures. He's applying the same force to the two different objects, right? So your acceleration is inversely proportional to the mass, right? So if you apply the same force to two objects, the one that's heavier is going to accelerate slower or at a lesser rate. Right? So that's why the lawnmower has the bigger A that goes with it, because it's lighter, so it has the larger acceleration for the same net force. Are we okay with that? Any questions with Newton's second law? So I'm going to guess that you spent a lot of your time with this last year, F equals ma. That's where I believe grade 11 spent a lot of their time. Okay, so look at the next slide here. So we take a look at this question here. Jessica's skydiving when she opens her chute and falls at a constant speed. At this time, the only force acting on Jessica and her chute is gravity. So if we take a look at this question here, not that it necessarily relates to Newton's second law, but it's more of a knowledge and understanding type question. So which law does this fall under for Jessica here? She's skydiving, and you can read the sentence yourself. Does this fall under Newton's first or second law? Eric? Pretty sure it's first?
I just know it's false.
Pardon?
It's false, and I think it's first.
Okay. Does anyone, how many people, other people think it's the first law? Supports Eric here. Anybody think it's the second law? How do we know it's the first law? Eric just thought that it was the second law. So you're right, sorry, first law, and it is right. And?
She's falling at the constant speed, which means no acceleration.
Yeah, perfect. So the word constant speed is your indicator, right? Because there's no acceleration, so that makes it the first law. So what would balance out her force of gravity then? Jake?
The air resistance.
Air resistance or something, right? It has to be an equal force going up. How about the next one here?
Wait, was the first one false?
Yeah, first one on the fall. How about this one? This is a problem question that relates to Newton's first or second law. Sloan?
First law.
First law? Okay, how many people think it's the first law again? Ooh, less convinced there. Only 3 with you. Are the rest of you second law then? How many second laws do we have?
Isn't it? I think it's kind of both, isn't it?
Is it though?
Maybe it's more first than second.
So what do you think it is? Well, what are the arguments for the first law?
That an object in motion stays in motion, so she was in motion, but the bike stopped, so she keeps on going in motion.
Yeah.
Something stops her.
Okay. And what's the argument for the second law then?
Well, she's probably like accelerating when she falls. I don't know. Maybe not.
Oh, I know. Wait. Let me think. Okay, so I think she accelerated forward because of the force and the mass.
That's what I'm asking you. You just asked me a question back. Jake?
Well, like I think it is the first law, but like an argument for the second law. When she hit the car, the bike rapidly decelerated.
Yeah. No, I like that too. So Andre, your answer for the second law is after the collision. So you're not wrong, but we're looking at like the time of collision,
Okay.
right? So then Jake brings up a good point. It's what object are we looking at? Are we looking at Hannah or are we looking at the bike? Right? Because if you look at Hannah, that would be a first law answer because her inertia keeps her going. So she's not thrown over the handlebars. It's just her inertia keeps her going while the bike stops underneath her. But you could look at it from a second law point of view where the bike is slowing down quickly because it does hit the car. So if we look at that object, that would have a different answer. Right? So it's important when you're reading a question that you understand what the object is that you're looking at so you know don't look at the wrong one. Good answers though. We talked about this already, right? For Newton's second law, we really need to focus on, take that back. If you would like to, you don't have to, but I do, is I always focus on putting the positive x direction in the same direction as my acceleration. And the reason I like to do that is because when I do my math, my acceleration is not in components. It's always whatever I work it out to be. It doesn't mean that you can't do it in a different way. Some ways are easier than others, as we saw with Andre's answer up there. This is something that works for me, but it may not work for you. So you have to find something that works for you. So we did touch on this last week, right on Friday, but maybe you weren't focused on it. So I just wanted to go through this again. So when you look at this box on a ramp, right? Depending on which way the box is going, you would make your acceleration make it fit. Right? So if we said that's a frictionless ramp, that there's nothing pushing on it, that's powering it up, pushing it up the ramp, right? We would say that the acceleration is going to be going down the ramp. So our positive x direction, in my eyes, makes sense to me that I'm going to say the positive x is going to be going down the ramp. Okay? And my positive y is always perpendicular to the acceleration, and I like to make it always the same direction as the normal force, so I will make it straight out of the ramp. Okay? If we look at the baseball player down here in the bottom corner sliding into second base or wherever that is, right? You can see that, and you know if you're looking at the picture there, that the baseball player sliding is slowing down, right? You don't slide to speed up. So when he's slowing down there, that means that his acceleration is going in the opposite direction that he's moving, right? So it's going backwards. So I would make my positive x direction not the way that he's moving, but I would make it in the direction that his acceleration is, which is backwards. You got a sprinter here, right? The sprinter, as we know, is accelerating down the racetrack, right? So we would be doing it same way, right? And it doesn't, my arrows don't really fit that picture because it's kind of coming out of the board at you. But again, our positive x direction would be in the direction of the acceleration. Any idea what force causes the sprinter's acceleration? Just as a side note. Jake?
Would it be the normal force of them pushing off the thing?
When he pushes off the thing, yes, and then once he's off the starting blocks, then what is it? When you walk, what is the force that causes you to move? Slow?
It's friction.
Friction. Which type of friction? Pardon? It's not kinetic friction. Static, right? Because your feet don't move when they're on the ground. So it's a weird scenario though, because you're used to, or for some of you always think friction acts against your motion, right? But in this case here, it's causing his motion because it's against his shoes slipping out behind him. So it actually causes him to accelerate forwards. But we'll touch on that more when we do acceleration. I have a person with a suitcase here, right? And in terms of the person in the suitcase, we have our acceleration, if he is accelerating, would be going forwards based on what he's looking like there. We don't know the rest of the story. But I wanted to emphasize this one because when you draw your free body diagram for this one, you would have your normal force, or force of gravity going down, your normal force going up, some sort of friction probably going backwards, and our applied force is on an angle. So when we rotate our coordinate systems, right, you can see that 3 of the 4 vectors here match up with one of our axes on our coordinate system. So we just have to break down the applied force into components. So it just makes the math a bit easier when we work with components. That's it. So the shifting of the coordinate system is new. So we have to get used to that, and that's what the purpose of the next picture, or our first example of the day is for. We'll actually do 2 on angles, just to start getting used to it. Any questions with the rotation part though before we actually apply it? Okay. So let's do this together. Okay, so we have Sophie sits on top of a frictionless snow-covered hill on her inner tube. If the hill is inclined at 25 degrees to the horizontal, what will her acceleration down the hill be? Okay? So, if we take a look at this question, right? I'm going to give you guys 2 minutes to draw your free body diagram and your system diagram. Go. All right, time's up. That's the answer. Okay. So, what's your picture look like? Maddie, which way does your hill slope? To the left or to the right?
To the right.
To the right? Okay. So we have a hill. So your hill might look different than this. So Maddie did hers sloping to the right. So we have the tube. Sophie sitting in the tube. Right? So she's going down the hill. Okay? Again, you don't have to do anything. Yours could go the other way if you so choose. The only reason it's important is because when you're do your free body diagram in a second, it's going to match this. Sophie, what does your free body diagram look like?
FG is, I don't know if it's like perpendicular to the X or it's straight down.
Straight down. FG is always straight down. And what else do you have?
FA is like the direction of the X.
Nope. No FA. If you don't have a friend pushing you, or a friend was pushing you, then you would have FA. What other force do we need in our diagram here? There's only one other one. Maddie? Which way is that going?
Up from the hill.
Yeah, up from the hill, right? So your normal force points straight up from the hill. Let's just call it that way. Okay? So your normal force points perpendicular to the hill. Gravity always points straight down. Which component do we have to put into, what vector do we have to put in components? The normal force or the force of gravity based on our coordinate system? And my poor drawing, don't let that help you out. Eric?
I just wondering, is there any type of friction involved?
No, because the question said frictionless hill. Which vector? We have two choices here. We have the normal force and the force of gravity. One of those is in components and one is not. Which one do you think it is? Jackson, which one would you get? Which one doesn't match our coordinate system?
Gravity.
Gravity, right? So gravity has to be in components because it doesn't match our coordinate system, right? The normal force should be in the same direction as y. Obviously, mine's not exactly the same because I'm not good at drawing, and neither should you be. So that makes our gravity the one that needs to be broken into components. So we can do that together. So our gravity vector is going to look like this. We'll have FGX in the bottom, FGY on the side here. Is that too small for you in the back, Maddie, or is that good? It's good, okay. Right, and our angle that we need to know is this one up here. So the angle at the top is 25 degrees. It is always the angle at the top where the angle goes. That matches the slope of the hill. Do you care why it's there, or are you okay just knowing that it's there?
Why is it there?
So why is it there? So when you take a look at it, how can I show you? So I have my coordinate system X and Y, normal coordinate system, okay? So under the normal coordinate system, it would look like this on the slope. So what I'm doing is I'm taking the x-axis, which is the clear ruler, and I'm tilting it so the slope, so it matches the slope of the hill. Does that make sense so far? Everybody can see that? So I've tilted this 25 degrees up, this one here, to match the slope of the hill. So in doing so, that's taken this one here, and moved it 25 degrees that way, clockwise, if you want to call it that. Right? So I'm taking my normal slope like this and rotated it 25 degrees clockwise. Does that make sense, everybody? So now you know, but if you forget, just memorize the top corner is always where the angle goes for the slope. That is it. Okay. If we go through this, we don't have any other information. Does anybody feel like I forgot something? So Eric feels like it. Anybody else feel uncomfortable with the situation? All we have is our angle. Right? Didn't put a mass in there. Didn't put anything else in there. You guys feel that's okay? You just feel like I made a mistake. Anybody feel like I made a mistake? I know Eric does, because he already said yes. Nobody else does? I would, if I were in your shoes. Because what's our equation that we use for when things accelerate?
F equals ma.
F equals ma, right? So our equation, so we put a little x in there just to remind us that we're only accelerating in the x direction. We're not accelerating the y. And we have it equal to ma, but we weren't giving m in the problem. So that might cause some stress if this was a test situation. You're like, I need a mass. Mr. Arkell didn't give me one. Why is he trying to make my life tough by not giving me a mass? So we take a look at this, right? What force is causing our acceleration? When we look at our free body diagram, what force or forces is causing our acceleration? Jackson?
Gravity.
Be specific. You're right, gravity is part of it, but not all of it. Andre?
It's the force that's pulling it down the slope. So is that gravity or is it FA?
No FA, right? There's no way pushing this over here. Ethan?
Is it this FGX component?
Yeah, good. So it's FGX, right? The FGY component's not doing us anything in terms of acceleration. We're only concerned with arrows that point in the x direction. Right? So that's why a free body diagram is really important, because you just have to, once you have it right, if we're doing our net force equation, we're only worried about things going in the x direction here, or down the slope, parallel to the slope. So we have FGX equals MA. So we don't have friction, so that's not involved there. We don't need the normal force, so that's not in the x direction, right? They're two independent of each other. What equation do we throw in for FGX? What's the equation for FG?
Mass times gravity.
Yeah, mass times gravity, so we have mg. And how do we deal with the x part? What do we replace that with? Sloan?
Is it sine 25?
It is sine 25 because it's the opposite angle. We have sine. Is everybody okay with how we got there? So FG is the hypotenuse of the triangle. Remember that this is a right angle triangle in here where the hypotenuse is here. Right? So that's where the mg comes from, and then sine is because it's the opposite side. And lo and behold, our masses cancel out because each term has a mass in it. So we actually didn't need the mass for this equation, so everything's okay. And we can find our answer here. Right? A is equal to g sine 25, which is 9.8 meters per second squared. Sine 25. And that was 4.1. So So I think most of the questions will ask for the magnitude of the acceleration, right? If you want to put the direction in, you would just say down the hill, because that's what it is. Any questions with that? There's a lot of thinking going on there for a math answer that is nowhere near as hard as we did yesterday, right? But yeah, it takes time to think it through. And if you're a person whose strategy is to find like the force of gravity somewhere else, so I've seen students who like, okay, Fg, then over here on the right, like Fg equals mg, and then find what the number is in Newton, right? That you're going to run into difficulty in this question because you don't know the math to do it. And if it was a test and you asked me, sir, you didn't give me the math, my answer to you would be just make one up. Because it doesn't matter what mass you put in there, it's going to cancel out anyways, and you'll still get the same answer of 4.14. Right? Because really that answer is telling you that it could be a mouse or it could be an elephant. There's no friction, all the objects accelerate at the same rate down the hill. Right? Which is counterintuitive because the mouse would not go as fast as the elephant. The elephant would accelerate faster. In real life. Probably. Are we good? Any questions? Ready for the next one? Okay, so the next question is from an old exam that only 2/3 of my class got correct. Because the third that got it wrong made a very simple mistake. And I found that classes that I tell that to, usually everybody gets it right. So I'm expecting the same out of you guys. So if you take a look at this question here. Annabella takes a ride on a hot air balloon. The combined mass of Annabella and the balloon is 350 kilograms. They accelerate upwards at a rate of 5.5 meters per second squared. What is the force of lift acting on the balloon? I give you 5 minutes to answer this question. Go. I didn't put the answer up there because I want to see what your answer is. Does anybody else have the your bio sheets that I gave you last week that you're supposed to take home and get signed by your parents? If you could you bring them back tomorrow? Maybe I'll put a post on D2L just to remind you. I have to collect them all from you guys. All right, we're good? Anybody need more time? I'm gonna do the question myself so you can check your answer. Let's see here. Anybody get 1,925? Anybody for those answers? Okay.
You said 9,000?
Pardon?
What did you say?
1,925?
That's it?
No, did anybody get that?
Oh yeah, I got that.
How many people got that answer? Okay, so you're in the third, 2/3 or 1/3. Sorry, you're in the 1/3. They got it wrong.
Oh, are you saying the final answer or part of the answer?
The final answer.
Oh, that's what I got.
Okay, let's take a look at this question. And what was the answer? Did anybody get? What's the other answer? Jake, what'd you get?
5,355 meters.
Yeah, I think that's right. Yeah. Okay, so when you are doing this question, right, you have to draw a good system diagram and free body diagram. So if we have our balloon, right, so here's my balloon with the basket underneath. And we know it's going upwards, so my acceleration is going upwards. All right, so just being picky for me, and again, you don't have to do this, but I can say positive x is going up. So my free body diagram, I have the force of lift going up and the force of gravity going down. Right, there's no normal force because it's not on the ground. There's no applied force because it got replaced by the lift, the word we made up there. Okay, so if we take a look at what we know the mass is 350 kilograms and the acceleration is 5.5 meters per second squared. So the mistakes happened on the exam when students were rushing. They didn't take their time to look at their good free body diagram that they drew. Right, so you can see in the positive x direction there's two forces, right? The lift force going up and the force of gravity going down. So when you do your net force equation, right, you have your lift force going up and the force of gravity going down. All right, so in that case, the group that got the first answer, right, did FL equals MA and then just did the math to get the answer. So they got 3 out of 5 if they showed all their work. Right, the people who got 5 out of 5 made sure gravity was there, and they have MA plus MG.
Please excuse this interruption. Good morning. Shortly we will be having our first of 3 fire drills for the semester. Unlike drills in the past, we will not all exit at once. We are going to ring the bell for a short time at 9:15, and then it'll stop. This will help students to recognize the alarms should it sound. When the bell rings, please remain where you are. Again, please remain where you are as it is just for you to hear the bell. In order to respect distancing protocols, we will practice the exiting of building in grades. We will make an announcement when it is time for your grade to exit. As you exit, please ensure you are maintaining physical distance. Please use the closest stairwell regardless of directional arrows and use your assigned fire door exit. Teachers, please review the plan with your class. Once you are outside, please keep your class together and maintain distance. An administrator will indicate when you can return into the building. Thank you in advance for helping to keep our community safe.
So are we okay with that answer? Andre?
Quick question. Since gravity is going down and the force up is going up, why are you adding them? Is that how you rearranged it?
Yeah, so here, right, the lift force is up, the gravity is going down, that's why there's a negative sign here.
Yeah.
Right? And then when you to find the lift force, you gotta bring that to the other side, which makes that positive. Right? But then just put your number. Sometimes it's good to put a negative here, but you don't have to because you already included it here when you did the math. Okay? If you did it a different way, still got the right answer, then that's okay.
It is now time to exit the building for your assigned fire exit. Please gather socially distanced.
Because I said X is positive going up. If you called it Y going up, then it would be Y, and it's still the same.
Okay, good.
That's what I told you. Like, I do it, this is my way, your way should be different because it should make sense to you. Right? I told you at the start, like, I always make positive X the direction of my acceleration. So in cases like this, it just looks weird. But if you want to call it Y, like, you're not wrong. It's just different. Different is good. Are we okay with the number of the answer? Everybody sees how they got it? Again, the kids on the exam that didn't get full marks forgot the gravity. So just be careful when you think through the problem. Alrighty, I'm going to erase that. We have one more example. Try this one on your own. And we'll take it up together. And the answer's up there this time. So,
What is the map?
It's like the hill. Pitchers pitch from it, baseball. You ever watch baseball?
No, not really.
So they stand on a little hill.
So like, if you want to,
Yep.
and what is the level of the line?
Straight.
Oh, okay.
Yep. Wrong.
When we have to exit, we go through this door, down the pony stairs, and out the door to the front park or the parking lot back here. Is there any place you guys want to meet in the parking lot that you feel passionate about that we'll all be in the same spot? We'll go outside, we'll pick a light standard. So you pick one that was struck by lightning, that would be good. Alright, so we have our motorcycles going up the hill. It's going to go off the jump. But make sure that when you do that, again, my rule, positive X goes in the direction of the acceleration. And when you do your free body diagram, that you do it large enough that you can see all the components. Right, so in this case here, I specifically asked this question because I wanted to test if you knew how to break their FG down into components. And added a force of friction this time, which we didn't have before. and I made up the ramp positive because she's accelerating up the ramp. So when you have your free body diagram, right, that's the hardest thing in my eyes in these questions, is making sure you have that right. Because once you get that right, if you have that right, the net force equation should be easier to get to, because when you start with, okay, it's accelerating in the x direction, right? So we say that, we know it's accelerating in the x direction. So then we just look at any arrow that matches what we said was positive x, right? In my head, when I think through this, I'm thinking, okay, what's causing me to accelerate? What's causing the object to accelerate? I look for that first. So in this case here, FA is causing Sloan to accelerate. So I put FA first. The next question I ask myself is are there any forces slowing the object down or preventing it from going as fast as it could? So I have to look for arrows that are in the opposite direction that I said positive X. And I'm only looking at those. So here I see this is going the opposite way, so that's force of friction, so that's going to be negative for me. And I see FGX, because it goes down and across. It's also pointing in the opposite direction. So I have an FGX in there too that equals MA. So I have three forces here, one positive, two negative. So that's all fine and good. Then the next thing I saw, for some who are struggling, that we had like the, was it 1,000 newtons somewhere? Or that's friction, never mind. So you have FA minus 1,000 newtons minus mg sine of the angle, whatever that was, equals MA. So I saw
All grade 12 classes, it is now time to exit the building to your assigned fire exit.